All right, so I'm going to briefly show how to graph the derivative function. This is for 3.1b in your notes. All right, so over here on the left, this is your original function right here. And let's see, make sure you can see it. All right, and we are told at certain points what the slope of the tangent line is at these different points. So right here, when x is 0, the slope is 4, right here at this point, 0, 1. And at this point right here, at point B, they're saying that the slope is a 1. That means if I were to draw a tangent line right here, the slope of that tangent line would be a 1. Right here, up at the top, this maximum, the C point, if I were to draw a tangent line here, I'm told that the slope would be 0, so that's a horizontal tangent. Notice that as the curve starts to decrease, my slope values are going to be negative. So at D, the slope of this tangent line that I would draw would be a -1. Over here at E, it's also -1. And down here, you were told that at point F, the slope is a 0. So it says sketch the derivative over here. Now here's what you draw with your derivative. Your inputs are the same inputs that you have here, but your output is the slope, okay? Input has the same x values, but the output value is the slope value that you have there. So at 0, at x equals 0, the slope is a +4. So over here, I'm going to go 0 up at 4 and plot a point there. And then the next point, I said it's about 1.5 right here. And so this one has a slope of 1. So at 1.5, the slope is a 1. So I'm going to put that right there. So this one here, I'll just label it as point A. This one is B. Let's see, the next one, point C, is at 2, and the slope is 0. So that's going to be a point right there. So there's C. And the next one is at x equal to 3. The slope is -1. So that's going to go down here. And the next one, that's D. And the next one is at x equals 5. The slope is a -1. So that's here. And then at 6, the slope is 0. All right, so this is E, and this one here is the F slope. All right, so what I'm going to do, I'm just going to connect these points here and draw a curve. It looks like this. All right, now let's see. It says suppose the function represents the depth in inches of water in a ditch alongside a road as a function of time. So this is how deep the water is over time. So this is the depth of water. So this is inches of water. Inches of water. And here we have time in days. All right. So it looks like this is like 1 inch of water, and then over 2 days it goes up to about 4.5 inches of water, and then the water starts to decline in the ditch. All right, so it says what happened, describe what happened to the water in the ditch over the 7-day period. So I just basically said that the water increased to 4.5 inches, and then it started to decrease through to day 6, and then it looks like it probably started raining again, and so the water started to increase. All right. So what does the graph of the derivative represent? Well, these are still days over here. But remember, the derivative represents the slope. So if we come back over here, we're going to put y units over the x units. So the outputs here now represent inches per day. All right, so f prime of x represents the rate at which the water depth changes. So it's different. This is a rate at which the water changes at any given time. The water rose quickly on day 1. You see, because it has a very steep slope. The slope is high, so it's changing faster here. And then the rate starts to decrease. So it's raining heavy, and then it's starting to slow off, not rain as much, right? Because it's starting to peak right here. And then the water level starts to go back down. So maybe it's hotter, it's not raining, it's starting to evaporate, and then it starts to increase again. And so then stops increasing on day 2. The water level then fell until day 6, where it started to increase again. So you could say possibly it was raining. So the units for this, for the derivative, is inches per day, time in inches per day. All right, this is the second example saying sketch a graph of a function. So we know the following properties. We want to sketch the original function. We want to graph f of x. And here's what we're told about f of x. This first one says f of 0 equals 0. That just means the following point, 0, 0, is on my graph. So if here I want to draw my original function, I know that 0, 0 right here is on my graph. That's all I know so far. Now the next part, I'm told that the graph of its derivative is shown over here. This is its derivative function, which represents the slopes of the tangent lines of my original function. Now notice here, from x equal to 1 and to the right, the outputs here are constant. They are all 2, right, everywhere. So this would mean that my original function, all of the slopes, every single one of the tangent slopes from 1 over are 2. So that means really at x equal 1 that I'm going to have a line here that has slopes of 2, but I'm not really sure where it goes yet. I need to know this information here, because to the right of 1 doesn't go through this point right here, so I'm not sure where it goes. So down here, this bottom piece derivative is telling me for values of x that are less than 1, all of the slopes of the tangent lines are m equal to -1. Now notice this derivative function goes through where x equals 0. So this means at x equals 0, the slope of the line is -1. So if here's 0, 0, and I know that is a point on the line, I know that my slopes of my tangent line, since this is flat and constant right here, that means every single tangent line is going to have the same slope. So I'm going to draw a line with a slope of -1 until I get to right here at x equal to 1. And for now, I'm just going to put an open circle because I don't really know what's happening there, because notice that these are all closed or open circles. So I'm going to draw a graph where everywhere on that line the slope is a -1, because that's what this derivative function is telling me. From x is less, all the values of x less than 1, the slopes of the tangent line everywhere is -1. And that would be a solid line like that. And then to the right of x equal to 1, all of the slopes are 2. So from here, I'm going to just go up 2 over 1, and now draw a line that has a slope of 2. Now, oops, here we go. All right, so here I have a slope of -1 everywhere. Here I have a slope of 2 everywhere. And this last part says the function is continuous for all x values. That means I can't have any breaks or holes, which means right here, notice that I can't find really what the slope is at that particular point, because on the left side of my point, the slope is a -1. On the right side of my point, it drastically changes to a +2. There's no gradual change in the middle. So I'm just going to fill that in with a point, and now I have my solid function. So in summary, if f of x is increasing, notice here my function here is increasing. It's going up as you go from left to right. This is called increasing behavior. Notice that the slope, or that my derivative function, is positive, right? And over here, notice wherever my original function is decreasing, then my derivative function has negative outputs. They're all down here. And I think that's it.